So, this is CNET 141, and today we're going to talk about elliptic cryptography. And the last lecture is next week, TLS, and there's class after that, but I won't introduce any new material. It will just be for people to catch up. There are a bunch of special events coming up starting tomorrow. I highly recommend coming to these. Tomorrow is Caitlin's guest lecture about red radio frequency, and Wednesday is Kaz's lecture about Kubernetes. And then on Saturday is the CCDC Invitational. And this being an invitational, there are no rules. Everybody's welcome. You don't have to be a full-time student or indeed a student at all. Anybody that's interested can just show up and participate. We're going to have a network of about 8 computers, and you'll be protecting them from Caitlin, who will be hacking them. She's on the red team. And so it's very instructive, very much worth doing, and you'll get some extra credit. If you feel like showing up, just there's instructions here to show up. And by the way, there is another event coming up down here. The embedded capture the flag is coming, and we'll have to have a team formed by mid-December. And then the event actually goes for almost the whole next semester. And it's worth college credit. It'll count as like a 197 project or something. And you have to write some kind of Python or C code to protect embedded systems, I guess. I don't know exactly what it is, but I think it'll be certainly very valuable. And students who want to do it, contact Lan Che. She's setting it up. So anyway, those are things to check out. And let's get to the elliptic curve cryptography, and then I want to demonstrate post-quantum cryptography. Just today, I finally got it working. So I go with the first post-quantum cryptography project, and I'll demonstrate that later. So let's talk about elliptic curves. We're going to talk about what they are, how they work, and how things can go wrong, just like the other chapters. So this basically is a replacement of RSA. Now, RSA is pretty good. RSA does have some flaws. There are like some bad numbers you can choose which make it vulnerable, and sometimes people don't pick those up well. And also, the main thing about it is that the keys have to be really long, like 2048 or 4096 bits, and that means it takes a lot of computing power. Elliptic curve cryptography is much, much faster because the keys are much smaller. So, however, since there was RSA, which was good enough, as you've heard me say in every chapter here, when a new thing comes out that's better, nobody really cares if the old thing is good enough. They just stick with the standard, and that's what people did. So it took a long time, until maybe like 10 or 15 years ago, before people started adopting elliptic curve cryptography. And, all right. So, an elliptic curve. This is the equation for elliptic curve. Y is a cubed plus ax plus b. And for some values of a and b, you get something like this, where in this region, if a and b are negative, there's negative numbers and you can't take the square root, so there's no real value of y, but you get a curve. And so the point is, this is the analytical, continuously varying version, which is not what matters to us. What matters to us is on integers on a ring. And in that case, you just take a point, and then you change it to another point, and it goes around the ring. So this is a module, this is a group containing 191 points, and the elliptic curve transformation will just change it from one to another. That's all it is, and you don't really care about how it works. That's just a field. So a field is when you have a set of elements, and the elements have, in our case, we don't have addition and multiplication. So we need to have 0. There has to be an additive identity element, so if you add it to any element of the field, you get the same element back, x, and there should be an inverse for addition, which when added to x gives you 0, and for multiplication, 1 over x, which multiplied by x will give you 1. A group with these properties is called a field, and if it has a finite number of elements, it's called a finite field, and that's what we care about, are finite fields. So, then you just have to, so all you have to do is have a set of these elements and then define some kind of operation, like addition and multiplication. And so here's how you define addition in elliptic curves. You draw a line connecting the points P and Q, find the point where it intersects, and reflect around the x-axis. So that means if P is here and Q is here, you draw a line, you find the point where it intersects, and you reflect it down here. So that's what P plus Q is. Now that doesn't much resemble addition of integers, but it doesn't matter. From a viewpoint, all we care about is you have a field, which is a set of points, and you have some way to combine two of them to make another one. And then it just has to fulfill certain mathematical properties, and it will do for cryptography. So you have a minus p. if you add p and minus p, then you'll get a vertical line. Here's p and here's minus p. So that'll give you a vertical line, and the place it intersects is out at infinity. And so in every direction, infinitely far away, is the same point called the point at infinity, and that's what counts as 0 for elliptic curves. That's why it doesn't resemble normal addition and multiplication a whole lot, but it is a way to combine points to get to another point. And if you add p to itself, p plus p, then you use the tangent line and find where it intersects and reflect it down here. So again, p plus p gives you something else, and that's all that matters, is you have some way to combine points to get another point. And so you can now multiply. You can multiply a constant times p by just adding it many times. Now this can turn out to be pretty expensive, so you can of course make it faster by calculating p2, which is p plus p, and p4, which is p2 plus p2, and p8, which is p4 plus p4. So you can, instead of having to do, if you want kp, instead of having to do k operations, you'll have to do log to the base 2 of k operations, which is much less work for large values of k. All right, so a group is a set of elements, and x, y, and z represent arbitrary members of the group. You have an operation, and here's the properties. You have closure, so if you combine any two elements, the result is still in the group. You have associativity. You can do operations in one order or in another order, and you get the same answer. You have an identity element, so multiplying identity times any element gives you the same element, and you have an inverse. There's some way to multiply every element by its inverse, and then you'll get E, the identity element. That's a group. So elliptic curve has this property. P, Q, R in addition form the group. It's got closure, it's got associativity, it's got an identity element, which is the point at infinity, and it's got an inverse. For every p, if you take minus p, is the inverse. So if you add those two, you get 0, which is the point at infinity. So now you've defined the mathematical operation. And you know, in a way, it's amazing how close this is to RSA. It's like the symbols and the pattern of moving symbols around is like RSA, as we'll see. So here's the DLP problem. Given p and q, find a number you can multiply p by to produce q. That's called a logarithm. And this is believed to be hard, and it has turned out nobody has cracked it in 40 years, so it appears to indeed really be hard. So if you use field ZP where p is n bits long, the security is n over 2 bits, which means a 256-bit long field is enough to have 128 bits of security. That would take 4,096 bits with RSA, and that makes elliptic curves 20 times faster, 20 times less CPU to achieve the same level of security. So it's much more efficient. So you can now do Diffie-Hellman with elliptic curves. You start with a generator called G that they both know, which is an element of the group. Then this person picks a random A and sends G to the A over here. This one picks a random B and sends G to the B. Now they can calculate B to the A, which is G to the AB, and G to the AB. Now they can agree on a secret. This is exactly like RSA-based Diffie-Hellman, the same logic. And so you choose a fixed point G. The shared secret is DA-DB-G, and off you go. So that's the same thing happens. You end up with the same number at both ends, DA-DB times G, and nobody can determine the secrets from what's said over the wire without solving the hard problem. All right, so now you can sign things with elliptic curves. This is the digital signature algorithm. This is what's used in Bitcoin. That's why people often get excited that if you were to find a flaw in this, you could steal everybody's Bitcoins. But there's no apparent flaw in it that we found. So you have a private key D. Verifiers hold the public key. And you have to agree on what elliptic curve you're going to use, its order, and the base point, G. These is public information. And so then you hash the message, pick a random number K, and your signature is these two numbers. X mod n, which just comes from the random number, and here's where the hash goes. So I don't know why they do it. One number just comes from a random number, the other one has the hash in it, but the point is you do have some number which was calculated using the hash and your private key. which I'm having trouble finding the private key in here. D must be the private key. Yeah, D is the private key. So you use the hash and the private key to create a number, and it can be verified by people that only know the public key. So it accomplishes the same purpose. And again, it's much smaller. If the coordinates are 256-bit numbers, R and S are both 256 bits, and so a signature is 512 bits long, which is not very long. So RSA is used only for encryption and signatures. ECC has more. It has encryption and signatures, key agreement, and some other functions. However, as a disadvantage, oh, that's right, we're not going to worry about that right now. That'll come later. All right, so the RSA signature and verification algorithms are simpler. That elliptic curve process is a little screwy, but people have learned how to code it properly. But the major advantages is it's much faster to sign, and the signatures are much shorter. And here's the speed comparison. It's 150 times faster than RSA. So if you use RSA, a signature takes 7 milliseconds, but with elliptic curves, it's 0 to all this many places. And it takes, what is this, 0.1 millisecond to verify, and here it takes 100 times less. So it is much, much faster. Save a whole lot of CPU time. All right, now you can encrypt raw data with elliptic curves, but the problem is your key is only 256 bits long. You can only send a message of about 100 bits. So you can't really send much of a secret message directly encrypting with elliptic curves. That's not what you do. What you do is you generate a Diffie-Hellman shared secret, then you run it through a key derivation function to derive a symmetric key, and then you use AES or some other symmetric. Just exactly, that's called the integrated encryption scheme, where you include both public key encryption and private key encryption working together. That's how TLS works. That's how pretty much all of them work. So here's how it works. You pick a random number D and compute the point D times G. D is your private key, and Q is the public key. And you compute I think, yeah, then you, well, it's not, yeah, this is your secret is D. Then you take D times P, which I think came from the other person. You do a key derivation scheme to derive a symmetric key, and then encrypt it using a symmetric cipher. Yeah, all right. That just makes it a little harder to read, but it's the same thing you'd expect. All right, so now there's an issue of what curve to use. And here you get into some paranoid conspiracy theories, which really have had a big effect. So the parameters are the order, which is the modulus, and A and B in this function. And how do you choose A and B to choose which elliptic curve to use? The order must not be the product of small numbers, and it's handy if your curves can treat P plus Q and P plus P the same, so that the timing and other things about the calculation don't depend on which one of these you're doing. That might be a side channel to leak out information. But the main issue is how you choose A and B. And it turns out that NIST, the US government, specified 5' curves to standardize this in the year 2000. And they defined 5' curves. There's also 10 others that turned out to be less useful and almost never used. The 5' ones are the main ones people use from the NIST library. And the most common NIST curve is P256. So the modulus is P, and here it is. It's 2 to the 256 minus 2 to the 224 plus 2 to the 192 plus 2 to the 96 minus 1. So it's just composed of like a few bits here. So that's the prime number. Then you have Y, is 3x plus B. And this B is very strange. It's the SHA-1 hash of this long random looking value. And that's a problem. As before, NSA never explained how they got this value of B. And that started all people being paranoid and having conspiracy theories, feeling like they probably backdoored B because they absolutely got caught doing that before. And so even Bruce Schneier, who is pretty conservative, decided not to trust it. Let me zoom this up so Bruce Schneier wrote, "I no longer trust the constants. I believe the NSA has manipulated them. I looked at the random seed values. Here's this long, apparently random value. No justification is given. I now personally consider this to be smoking evidence that the parameters are cooked. Therefore, almost nobody uses the official NIST curve. They use ones that are not approved by the government because they're afraid NIST poisoned it. So they avoid the NIST-derived curves. Bitcoin, Tor, and many other things use other ones." And we'll talk about the other ones that are actually more popular, for probably a good reason. So curve 25519 is not a NIST curve. It was published by this guy, Daniel Bernstein, and it doesn't have any suspicious constants. So it is x cubed plus this number plus x. And 2 to the 255 minus 19 is the order you take the modulus of. This is used all over the place. Chrome, Apple, OpenSSH. This is nice. People regard this one as very secure and not poisoned by the US government. Here's another one used in Bitcoin. 2 to the 256 minus 2 to the 32 minus 977. And you see the A and B are very simple. A is 0, B is 7. And this is what Bitcoin uses. Again, a unapproved curve, considered quite secure. There are other curves. France had their one. Germany had them. Like us, Germany used constants that were never explained, so people are worried they might have poisoned it. And there's newer curves, supposedly more secure ones. A couple of them are out there, but as always, the previous curves are good enough, so very few people are interested in going on to the new curves, even though they might in principle be better. There's no real need for them until we find a serious flaw with the old ones. So, what can go wrong? Elliptic curves do have more parameters than Diffie-Hellman, so there's more chance of making mistakes or having side channel attacks, as the calculations somehow depend on the key and somebody who can measure the time or the electricity generated or the radio emitted from your device might be able to do something about the key. So that's possibly a weakness. And signing uses a secret random number, k, and as always, that's the nonce. You can't use it twice. If you reuse k, then they can calculate it, and this did happen to PlayStation. So this we talked about in almost every cryptography scheme. There is a random number you put in each message, and you're not supposed to reuse it, and if you do reuse it, it leads to a cryptographic flaw. This one is actually very cute and specific to elliptic curves. What you do is there's an attacker in the middle who's intercepting one of the traffic. They don't know the secret, but what they do is they send a malicious piece. You can use curves that are not good elliptic curves, curves that have a short cycle, so you can actually perform the hard problem. And so you can send a point to this person. Now they're waiting for a point to come on the curve, and they're going to multiply it by their value and send it back. And if they don't verify that the point is on the curve, they might be multiplying their secret times a point on a curve where you can solve the hard problem. And that's what you do. And this affected a lot of people. If the software failed to verify that the data that came from the other party was in fact on the right curve. So it caused you to leak out your secret. And that happened to a bunch of TLS implementations in 2015. So this is why, conservative places like banks will not even touch anything until it's been out there for like 20 years. Because even if the math is beautiful and it looks great, you got to wait to find out what the real flaws are. There are always flaws that appear years later, and conservative, risk-averse organizations don't want to touch anything unless it's been in use for 20 years, because you never know. There's always going to be flaws popping up like this. So let's try a Kahoot, which is here. Only 7 people in the Twitch. We may not have very many contestants here. I'll wait till the end of the song anyway. All right, so how long should the elliptic curve key be? 256 bits. All right. 1024 and 49.6, that's for RSA. You don't need that much for elliptic curves at all. All right. How long a message can you encrypt with AES? Any length, we've done it before. AES, just you have blocks of message, you can have as many blocks as you want. It's used to encrypt all the data you send over TLS. All right, which curve was suspected of having a backdoor? P256, that's the NIST approved one. This is the new one that's supposed to be better. All right. All right, so how long of a message can you encrypt with the integrated encryption system, ECIES? Any length, because it has a shared secret, it turns it into an AES key, and then it uses AES so you can encrypt a message of any length.